Hello, can you hear me? Okay, so we'll start with this colloquium. And it's a real pleasure to introduce Reshmi Mukherjee. Reshmi, she studied undergraduate studies in physics at the university, at the Presidency College in Calcutta. And then she moved to conduct the PhD thesis at the University of Columbia. After that, she went for a postdoc that she did in NASA, working with the Compton Gamma Ray Observatory and data from the egret detector on this satellite, and basically working in blazars. These are AGNs with the jet pointing towards you. Okay. Then after that, she moved to McGill University in Canada, and she worked in the STACE experiment. That was not very successful, but it was really interesting. And after that, she moved back to Columbia University, where she was faculty, and she's still there as faculty. She's professor of astrophysics. She has a strong interest in very high energy observations of AGN jets, and also galactic sources, unidentified sources, and instrumentation. And she is a member of the Veritas collaboration, the Cherenkov Telescope Array Observatory, where we collaborate on that. And also she is a member of the GRAMS experiment, a new satellite concept. And today she's going to be talking about exploring the extreme universe with gamma ray observatories. And it's a real pleasure to have Reshmi Mukherjee giving this talk. Thank you.
Thank you very much for the introduction, and it's a real pleasure to be here. So yes, I will be talking about, I hope you can hear me at the back, about exploring the extreme universe with gamma ray observatories. And so, as you know, gamma rays are the highest form of energy, and in fact, if you were to compare this with ordinary light, like a 100-watt light bulb, the amount of energy in an optical sort of band, gamma rays are much, much more powerful. They're like nuclear power plants times 1,000. So it really is a way for us to probe the highest energy processes in the universe. So the one thing that's happened in the last kind of 10 to 15 years is there's been a huge progress in the field in terms of the technology that we were able to develop. And I won't talk about some of these in my talk. But because of the progress in the field, we have really a lot of scientific results that have been really powerful. Yes. It's too much. Oh, okay, sorry. I don't know if I can fix that. Okay. Better? Okay. Okay, good. Okay, so just as I just wanted to quickly give you a little bit about my background because it kind of informs the talk. I started working on actually liquid xenon time projection chambers, and this was being used for MEV telescopes at that time. And so we didn't manage to really get much science out of it, but it kind of relates to what I'm doing now with liquid argon time projection chambers. And then I worked on the Compton Gamma Ray Observatory, which was one of NASA's 4 great observatories at that time. And what you see here is the egret satellite, and one of the first sky maps that we were able to produce at the highest energies. And this was the first time, I mean, there were missions earlier, but this was really the first time that we were able to view the sky in high energy gamma rays in a comprehensive way. And this sort of set the path for the current missions that we have at the moment with Fermi LAT and other space missions. And then I transitioned to mostly ground-based, and that's the subject of my talk. I mean, I thought I'd focus on the highest energies because this is what I'm doing now with the Veritas experiment. So I'll talk to you about that. And then the future is, we are kind of informed for the future with what we do currently. And so several of us are working with the Cherenkov Telescope Array Observatory, including people at this institute. So I'm sure you've heard about that. So I just want to start by acknowledging the work that my students and postdocs have been doing. And this is the group that I have at Barnard and Columbia. a large number of undergraduates, graduate students, and then I also want to acknowledge the work that I've done with my postdoctoral colleagues over the years, and a lot of the work that I'm showing here is actually work that they have done through the years, and just wanted to start off with that. So I realize this is a very general sort of an introduction, so I just wanted to step back and even start with what is gamma ray astronomy. So gamma rays, as you know, it's a really crucial window in the high energy view of the universe, and it's a way for us to really probe the extremes of astrophysical phenomena. And what you see here is basically a definition which is somewhat arbitrary. So you have low energy, high energy, very high energy, and then the units that I'm using are electron volts. So basically I'm going from 0.1 million electron volts to all the way to 100 TeV, tera electron volts, 10 to the 12, and even beyond. And it's somewhat artificial definition, but it actually is related to the techniques that you use or you need to use to explore the highest energy gamma rays, because as you know, the atmosphere is opaque to gamma rays, and in order to view the high energy sky, you really need to build satellite missions and send them above the Earth's atmosphere. And there's a whole series of satellite missions that are able to probe the high energy gamma rays, but they run out of effective area because you can only put such a large satellite, right, beyond which you run out of collection area. And so in order to probe the even higher energy gamma rays, you really need to do something indirectly. And so that's basically what we do with the highest energies is you use the atmosphere, the opacity of the atmosphere indirectly as a detector. So you can use techniques such as Cherenkov astronomy, and that's what I will explain today, is use basically the fact that gamma rays interact with the atmosphere and creates a byproduct of extensive air showers, which you can then use indirectly. So it really is basically a crucial window. It's the last sort of the extreme of the electromagnetic spectrum that is that you can investigate, and you can probe the highest sort of phenomena in the universe. So why gamma ray astronomy? And this is a slide that kind of summarizes, so in one page, if you were to ask me, can you summarize the motivations or the goals? Well, gamma rays are products of the environments that they interact with. So you can think of it as basically gamma rays are produced in situations where you have relativistic charged particles. You can have extreme environments such as high gravitational fields, particle acceleration in intense magnetic fields, for example. And what you see here is an image of what we call a relativistic outflow. It actually is the jet of a nearby radio galaxy called M87, Messier 87. This is in optical, but you can actually see gamma rays from this as well. So it is a way for us to probe these sort of situations where you have physics under extreme conditions. Gamma rays are also probes of the environment that they pass through. So because gamma rays interact, so for example, you can have extragalactic background light such as CMB or infrared, and gamma rays can probe with those background radiation indirectly, and therefore give you hints of the signature of the starlight or the extragalactic background light that exists in intergalactic space. You can also, for example, use gamma rays to learn about primordial magnetic fields, like the intergalactic magnetic fields, and you will see, because of the interaction of these photons with these extragalactic radiation fields, an imprint in the signature of the gamma ray spectrum that you measure at your detector. So there are indirect ways to probe the environments that they pass through. And then the other really strong reason is the ability to probe topics in fundamental physics. And this, in some sense, comes to us for free because we have this vast data set of high energy photons, which can then be used to probe, for example, the nature of dark matter. If you have, let's say, beyond the standard model particles, like, let's say, a WIMP, a weakly interacting massive particle, which could, if they exist in galaxy clusters, we haven't seen them yet, they might give you a gamma ray line in the range of the energies that we are looking at. And then there are other topics such as these hypothetical axion-like particles. If they exist, theoretically gamma rays could, in the presence of magnetic fields, interact with these, and you might see basically production of these E plus E minus, and again, you would see an imprint in the signature of the sources of the spectrum that you're measuring. So just see if I'm okay. So the outline, just to kind of orient what I'm going to be talking about. We just talked about the introduction and why gamma ray astronomy, and I'm going to focus on the origin of cosmic rays. I'll give you sort of a quick introduction of the instruments that are currently operating, that we are using as our tools, and the synergies that exist between these instruments. I'd like to talk a little bit about the science highlights. I mean, as you can see, the field is immensely rich, and I'm just going to be able to kind of give you just a very quick overview. And then at the end, I'd like to end with the future directions. So where are we going in the future? In principle, I mean, basically the Cherenkov Telescope Array Observatory, but then I'll also tell you about a new sort of beyond the sort of pushing the limit of pushing the envelope about a new idea of a dual mirror experiment. Okay, so the origin, if I just wanted to talk a little bit about the origin of cosmic rays, which still remains a mystery. So the relevant and I would say the still sort of the prime motivation for this field is understanding the origin of cosmic rays. And I think you may have seen this image, which is actually a photograph from the New York Times, very old, about more than 100 years old, which shows you Victor Hess, and he was on a balloon 17,000 feet high. This was, it was a very simple measurement, and the goal of the measurement was basically to look at the ion pairs. So the flux of cosmic rays is a function of altitude, and you can see there is an increase. And basically what this showed is that there is a flux of high energy cosmic particles from outside our universe, and so outside the solar system. And the question is, where are these coming from, and how do you accelerate them, and what gives rise to these cosmic accelerators? And we know a lot now, so we have actually been able to measure the spectrum. And what you see here is a very nice measurement compiled through the years over many different instruments. You see the flux on the y-axis and energy on the x-axis. And you can see if you look at it, it actually goes, this is in GeV, so in units of electron volts, it's basically 20 decades in energy. So it's a vast scale. It's a log-log plot. And you can see that basically it's an enormous energy range, which actually probes even beyond what we can do in terrestrial accelerators. These are mostly charged particles. You know the energy density is about 1 electron volt per cubic centimeter. So we're able to measure this really well. And if you look carefully, there's also a change in the spectral slope of the particles of the spectrum. And we think we know that the majority of particles that are up to, let's say, about 10 to the 15 or so are coming from galactic accelerators, and there are physical processes that can give rise to this explanation, that support this idea. At the very highest energies, the idea is that these have to be extragalactic. The magnetic field of the galaxy is not strong enough to kind of contain them, but increasingly, the nature of these particles up to the knee and beyond, which is basically 10 to the 15 electron volts, and we are calling these particles pevetrons, and the nature of these pevetrons is unknown. So where do you accelerate them? What are the sources? And what is the physics that accounts for the energy density that we see? Okay, so the goal is to try to measure the spectrum in gamma rays as much as possible at high energies. So this actually leads us to a whole different field in high energy astrophysics, which is multi-messenger astrophysics, which is basically the ability to use, in some ways, different ways to sense the universe. Because one thing you realize is that cosmic rays are charged particles, and because of magnetic fields that cosmic rays pass through, they are deflected, and so by the time they reach Earth, the direction of these cosmic rays are scrambled, and so you're not going to be able to point back to the source and figure out where they're coming from. So in order to explore the highest energy cosmic rays, you really have to use indirect neutral messengers, and you rely on the fact that the physical processes that give rise to high energy cosmic rays are also such, for example, in cosmic sources such as astrophysical jets and active galaxies and supernova remnants, you're also producing neutrinos as well as gamma rays. And by viewing these neutral messengers, you can actually learn about highest energy cosmic rays. So that's one of the tools that we are using. And in fact, when you view the high energy universe outside the solar system, you not only have access to gamma rays, you also look at cosmic rays, neutrinos, as well as gravitational waves, which basically is sort of the four pillars by which you can view or sense, in some sense, because for gravitational waves, you're really sensing it rather than actually directly seeing it. So my talk, of course, we will just focus on gamma rays. So we understand the processes by which you can accelerate these charged particles, and Enrico Fermi was one of the first ones to kind of work this out. And I'm sure, if you've taken a class in high energy astro for the students, you've probably done this Fermi shock acceleration, both first order and second order. But the idea is that you can have, in a supernova explosion, diffusive shock acceleration, where you have sort of a stochastic energy gain in collisions. You can get these shocks in supernova ejecta, in radio galaxies, and you can get these strong shocks where, or you can get a situation where you have strong magnetic fields, and these are randomly distributed so-called magnetic mirrors, where in the perspective of the particle, you're crossing the shock front with these head-on collisions, and you can gain energy. So there are, you can explain the cosmic ray spectra using the sort of shock physics such as this. The other big topic, the other big kind of source that is interesting is extragalactic jets. And this is something that I'm personally interested in myself, and I've been working on these for some time. So extragalactic jets basically are the regime of a relativistic plasma. This is basically where you can study high energy magnetized plasma, and these are, as the name suggests, extragalactic is outside our own galaxy. So these are not galactic sources. They can be very far. And what you see here, and these are amazing sources, they're powered by black hole systems. And what you see here is the pervasive nature of the jet of M87, which is one of the closest, about 20 megaparsecs. But the impact of the black hole in M87 is actually felt across basically 6 decades in energy scale. So you can see here, zooming in some units of parsecs, and several orders of magnitude larger jets. So you can see the jet across the electromagnetic spectrum through different instruments. And the latest, of course, I think you probably have heard about the EHT image of M87, which was really famous, and just zooming in. This is, for example, the jet of 3C273. This is another active galaxy. It's been well studied in gamma rays, but you see here the jet in radio, where you can actually image the parsec scale jet. And this is about kiloparsec scale, which at that distance is about 3,000 light years. So these jets are, this is where you have plasma astrophysics happening. These are magnetized. And some of the questions that we like to explore is, what keeps the jet collimated at such large distances? What kind of particles are you accelerating? Are these electrons or protons? And then what is actually the process? And then more recently, with neutrino astronomy, could these jets also produce high energy neutrinos? And then could the current generation neutrino detectors actually be able to see it? So these are kind of the sort of the broad sort of overview, goal, motivation for high energy astrophysics. And what I'd like to do next in the next few slides is tell you about the instruments and the techniques, okay? So what are the instruments at BHE? So this is kind of like a compilation of the current generation of the highest energy instruments that are operating. And you'll see here that we're actually very fortunate. We're working at a time where we actually have a plethora of instruments that are operational. And we can take advantage of the instruments as well as the synergies, because they're working at the same time. And so what you see here are the instruments that are the current imaging atmospheric Cherenkov telescopes, Veritas, MAGIC, and HESS. And I think you probably have heard about MAGIC, because there are many people here who are experts on MAGIC. And then this is complemented by the wide field of view instruments, HAWK and LASSO. And this whole thing is actually on a night sky map, so you can also see what are the dark spots sky in the world. And then recently, we also have this instrument called LST-1, which has just started operation and is already producing spectacular results, and is part of the Cherenkov Telescope Array Observatory. So what are the synergies between these instruments? So you can see here, this I'm just going to say the different kinds of instruments. And so what you start out with the satellite experiments. Okay, so satellite instruments, these are great because they are operational all the time and they can see the whole sky. They've been very successful. There are challenges. You have to launch them above the Earth's atmosphere. But we have one currently in operation, the Fermi LAT, which has been very successful. They're great for sky surveys because you can see the whole sky mostly, and they're great for transients because a transient is an unpredictable gamma ray event, such as a gamma ray burst, for example, which can go off and outshine anything else in the whole galaxy, but you can't predict it. So you're much better off looking at it all sky. But they also run out of effective area, as I mentioned. And so these are complemented by the high sensitivity instruments. These are the current generation imaging telescopes. They have exceptional sensitivity, but they have limited field of view. And in some sense, you have to know where you're pointing. And then the new experiments that are coming online are the large duty cycle, wide field of view instruments. And the main ones that I'd like to just mention briefly is the Hawk and LASSO. And these are the highest energy, sort of the limit of the spectrum. And together, basically, you're looking, although even just the gamma ray part of the spectrum, you're actually able to get several decades of energy across that whole spectrum to understand the physical processes that are going on. So how do these instruments work? Well, if I start with the highest energy, they rely on the physics of extreme air showers. So as you know, a gamma ray that comes in, it's a high energy gamma ray, the atmosphere is opaque, and it interacts with the atmosphere. It's just basically a transfer of energy and momentum. And you can have a gamma ray coming in and start an electromagnetic, basically an extensive air shower where the gamma ray turns into a electron-positron pair, and then it propagates down. And from the nature of the photon, the high-energy photon, you have forward momentum. The whole air shower is focused in the forward direction, and the particles are moving very fast because of the conservation of energy. Basically, they're moving faster than the speed of light in air, and as a result of that, you generate a shock wave, and that shock wave is called Cherenkov light, and you don't see it. It's very fast. It's in the ultraviolet. It lasts nanoseconds. But if you know it exists, you can use that towards building your detector. And then you have to be aware of the fact that in addition to the gamma rays, you also get cosmic rays, charged particles, protons, and they can start their own cascade. This cascade includes both electromagnetic as well as hadronic, and this is important because this is what gives, because of the multi-pronged nature of the interaction, it gives you a shower which is kind of broader and not as smooth, let's say, as a gamma ray shower. So here, the idea then is actually very simple. All you need is to build an instrument that can then be sensitive to the Cherenkov radiation. The physics of Cherenkov radiation is well known, and just from the properties of the angle of the Cherenkov light, the amount of light that's produced, all you need is an optical detector on the ground that then can image the shower. And what I have here is a little movie that shows you the red is the particle, the blue is the light, okay, the Cherenkov radiation. You can see you have a flood of light. It's about 100 photons per square meter on the ground. So there's a lot of light, and all you need to do is build a few telescopes, okay? The other thing to notice is the pancake nature of the light, which basically comes down very fast, a few nanoseconds, okay? So the idea then is, within this light pool, which is about 250 meters across on the ground, you can build as many telescopes as you want, but you're limited by funding at that point. So let's say most of these current generation instruments have between 2 and 4 telescopes, and then the clue basically is in the light pool. So the geometry tells you the direction of the photon, because you can image this light pool on your camera plane. Okay, basically you build a detector which is sensitive to photons and gives you a signal. The intensity of the light has the clue to the photon energy, and then the shape is important for cosmic ray rejection. Okay, and so what you see here is an actual image taken recently with an Astri. The name is not important, but basically the Astri horn camera, and you can see here each one of these blue sort of squares is, you can think of it as your camera. Okay, And the light here is some units of, it's actually photoelectrons, but it's some unit of charge, which gives you the shape of the shower as it's flashing through the camera. So the idea then is to actually be able to record these. And then the other big challenge, and this is something that the current generation instruments have done really well, is to be able to tell the difference in this amount of data that you're getting between a gamma ray shower, which is coming from your astrophysical source, and basically an overwhelming cosmic ray background, which it's about 10,000 times more cosmic rays than you get a single gamma ray. So the ability to distinguish between a very clean gamma ray shower and this is again a computer simulation of a proton shower and let's say a carbon nucleus of what it might look like on the ground. And you can then use this basically from the physics of the shower. This is basically students' PhD thesis where you really run the simulations, you understand the differences, you see how much light is produced, and then you can then kind of distinguish between what is the smooth distribution of photons on the ground. So you can see here, this is 500 by 500, and then what you might see for let's say a proton shower, which is much more blotchy on the ground. And then you can then use that to look at what it might look like on the plane of your camera. Okay, it's a much cleaner shower for a gamma ray. So this is a 1 TeV gamma ray shower, and this is a 2.6 TeV simulated proton shower. Okay, and so by teaching your analysis, and this was done many years ago by the first generation instruments, including the Whipple Observatory, and this is the original image by Hillas, and some of you may know his name. Hillas, basically, we named this technique in honor of Hillas. We call it the Hillas parameters, and you can see basically it was a very simple technique where you take the image, you parametrize it. You can parametrize it with an ellipse. You can calculate how much charge, the size of the ellipse, and here is a hand-drawn calculation. And basically that gives you the ability to distinguish. And so you have confidence in your measurement that you're not seeing cosmic rays. You're actually looking at basically signal from your source. So this technique, of course, has become much more sophisticated, and we use machine learning now to be able to do this. We use image template analysis, and the future generation missions will spend a lot of time. But this is the ability to do this well is what gives you confidence in the measurements that you make. Okay. So I just talked a little about these instruments here, which image the Cherenkov light pool directly on the ground. In order to go to even higher energies, we use air shower detectors, which are basically high up. You build these and you put them high on top of the mountains, and you can then, for the highest energy showers for the electromagnetic cascade, you can directly image the shower in instruments that you build. And there are two such. There's one called the Hawk experiment, water Cherenkov. So instead of using the atmosphere now, you're using water in tanks. Okay, so again, it's the same concept, but it's slightly different. And that gives you sensitivity to a much higher energy range and the ability to do all sky all the time because of the nature of the instruments. And the current sort of the state-of-the-art experiment is the LASSO experiment. And I think I was noticing that you had a recent colloquium from Zhen Kao talking about results from this LASSO experiment. So I'm not really going to talk about LASSO or Hawk other than to be aware of it because we can take advantage of the measurements from these high energy instruments. Okay, so I will talk about Veritas, which is what I work on, and what you see here is the night sky in Arizona. It's beautiful. It's a dark site. This is basically the Milky Way. It's one of the Veritas telescopes up at night. This is the galaxy that's up. We see the galaxy. We're in the northern hemisphere. Here, actually, you have a map. You can see this is the US. Here's Arizona, very close to the US-Mexico border. Okay, so you go on shift, you fly to Tucson, and then you drive down almost up to the US-Mexico border. And here are the telescopes. There are 4 of these. It's in the very remote. It's the Coronado National Forest. And we basically go there, and we have a program. We have a strong sort of a scientific program. And you can see here the details. You can see this is the mirror. There's 12 meters diameter. Of course, you don't build a 12-meter diameter mirror. You build tessellated mirrors, and you connect them. And then this is basically the camera, which is light-sensitive devices. These are photomultiplier tubes, about 3.5-degree field of view. But we take 500 million pictures per second, and then we keep the ones that, we basically do a rejection. There's a lot of analysis that goes in keeping, sort of identifying your signal. Okay, so this is, just wanted to show you what is actually a Veritas shift. I mean, if you're an observer, you know this. You go to the site, you spend all night, you stay up all night, you take data, you monitor the health of the instrument. This is one of the graduate students. And then the other big message here is that you don't, you need a coalition. You need a large number of people to build these instruments. And so you acknowledge the work of all of the 100 scientists, approximately 50% of whom are early career in terms of postdocs and students. And this is actually a photograph from one of our collaboration meetings. So I just wanted to give you one slide on the performance. I mean, anytime you build an instrument, you have to have confidence that it's working. And so the way we do that is we measure sensitivity. So here, for example, is a plot that tells you, so, basically we, loosely speaking, we compare the sensitivity to the ability of the instrument to measure something as bright as the Crab Nebula. So the Crab Nebula is a pulsar wind nebula system, which is very bright in gamma rays and across the electromagnetic spectrum. So for a source as bright as the Crab, if it's even 1% of the Crab strength, we can see it in 25 hours. So we can even see weak sources. For something that's pretty bright, like 10% of the Crab flux, we will see it in 25 minutes. Okay. So the takeaways here is that we have access to about 1,000 hours of dark time, and this is an average because remember we are sensitive to Cherenkov radiation, so we don't observe during the day. It's pretty much like an optical telescope. And then the other thing as a result of COVID, we were able to go fully remote. During the COVID years, we were actually able to run the observatory even remotely. And this is a plot that is a bit technical, but I just wanted to show you one thing here, which basically is that we monitor the health of the instrument across the years. And you can see here is the reconstructed flux of the Crab Nebula in units of modified Julian date, which is a way astronomers tell time, and approximately 5,700 is 1,000 is December of 2014. So across the years, we have a pretty steady sensitivity. So the instrument is working really well. Okay. So let me spend the next, the remaining part of the talk talking about gamma ray sources and the future. And I'll start with the sky map. And this is basically a sky map of all of the instruments currently operational. So using this technique, the VHE or TeV, very high energy gamma ray sky, we have about 300 sources. Okay, now 300 may not seem like a lot if you were coming from optical astronomy, for example, but for the people in this field, when we first started 20 years ago, there were 3 sources. So it was really a handful. And so we've come a long way. Each one of these point sources, you can see the legend here, is a kind of source. It's a particular type of source. They're from our galaxy as well as from outside our galaxy. I think the main takeaway here is not the number of sources, it's the kind of the different classes. The fact that we're able to see 10 different source classes kind of is amazing because it just tells us that almost any kind of source could be a gamma ray emitter. So it isn't just that you see active galaxies or supernova remnants. So the ones that are in red are what we call extragalactic sources, and these are basically a particular type of active galactic nuclei, which I'll tell you in a minute, which we think have supermassive black holes at their centers. Okay, so comparing this, I'd like to compare this with the GeV sky, which is the regime of satellite experiments. And it's always humbling for me to start with this plot because this basically is a satellite image from the 1960s with the Solar Orbiting Observatory. And this is a sky map with 600 photons, 600 individual lines. Each line is a gamma ray photon. So you can see here that when we started this field 30 years ago, there was really nothing. However, you can actually make out the galaxy right here. You could squint and say that is the galaxy. Okay, but of course we did much better because now we started, in the 1990s. several of us, including people in this institute, were working with the egret satellite, which is, and then what you see here is the GeV sky, and it's a very clear measurement of the galaxy in high energy gamma rays. You also see some of these extragalactic sources. And from where we started with 600 photons, we now have 1 million photons, 1.4 million photons, and many different source classes. And the idea here is actually pretty simple, because for satellite experiments, you can actually take advantage of the fact that a gamma ray of energy, anything above the pair production threshold, will pair produce. Basically, the primary mode of interaction for a gamma ray photon is to do E plus E minus. And so if you're able to build an instrument which has high Z conversion material, okay, you will be able to convert the photon into E plus E minus. And then you basically, from particle physics, you need a detector that can then measure the track. And so it's a very simple idea, and that's the idea behind these satellite experiments, and they worked really well. And now, we have Fermi, the Fermi Large Area Gamma Ray Space Telescope, which is in orbit. It's currently in orbit. It's one of NASA's missions, and it's been doing really well. And what you see here is a 13-year sky map of Fermi. And I mean, there's a lot of detail here which we can skip, but the red color is in the 100 MeV to GeV range. Okay, and you can see some structures here. I mean, there's the Cygnus X, which is a black hole system. You can see blazars, and you can see this big sort of bubble. I'm not sure you can see this in this light, but basically it's some sort of emission. It's actually 50,000 light years across, which could be powered by this black hole at the center of our galaxy. Okay, so the large majority of these sources that you see, in fact, with these pinpoints, each one of these blue dots, which are the highest energy, and you see many of these, are active galaxies. And active galaxies, this is the large fraction of these high energy sources are active galactic nuclei, which we think are powered by supermassive black holes at their centers. And basically, these have jets that are launched, and these, they're extremely luminous. The jets themselves are particle accelerators, and they derive their power basically from accretion onto a supermassive black hole. And these jetted AGN tend to produce these high energy gamma rays, and they have some particular characteristics. And in fact, the ones that we see at the highest energies are viewed directly along the line of sight. So it's like how you view them. This is getting into a little bit of detail about the classification. But the point is that with the blazars, you tend to view directly into the jet, and you're seeing the emission that's basically Doppler boosted. And as a result of that, you see certain characteristics, and I'll show you what that is. This is how we understand the physics of active galaxies, okay? So these basically they occupy a tiny fraction. The black hole itself, if you look at the size scales, is 9 orders of magnitude more compact than the whole galaxy itself. And this is where you have particle acceleration. I mean, these are the highest class, the largest fraction of the extragalactic source populations. And they exhibit ultra-short variability, sometimes minute timescales, very hard spectra. These could be particle spectra that can be very hard, which means that there's no cutoff as you go to higher and higher energies. And if you're seeing these high energy gamma rays from these distant sources, you do need particles that need to be accelerated to GeV, TeV energies in order to make this. Okay, and one of the big puzzles is how are you able to get this emission out in terms of from such vast distances. So what you see here are basically how we understand the gamma ray production mechanisms in blazars, and this is a hydrodynamic simulation of what might be like a rendering of a gamma ray jet, where you might have diffusive shock acceleration, Fermi 2, or recently there's a lot of work that's happening in understanding what we now know as magnetic reconnection, where if you have high magnetic field in the base of the jet, it is possible, and this is getting better and better with particle and cell simulations, to deposit a large fraction of the dissipated energy into this non-thermal flow. And this is being used increasingly to explain the physics of these AGN jets. So how do you get gamma rays out of this? Well, there are several processes. As you know, if you've taken a class in physics, I mean, there's Bremsstrahlung radiation. You can take synchrotron emission, for example, in a magnetic field. You can have something called inverse Compton scattering, where you have a low energy photon that's upscattered by interaction with a relativistic electron. Or you can have hadronic processes where you can have an incident proton in interacting with material like hydrogen, for example, in a molecular cloud that gives rise to pions, which then decay. Okay, so if that happens, that's what informs the spectrum that you measure. And so this is what we call the spectral energy distribution plot, which shows you energy as a function of frequency. And you can see this goes from radio all the way to TeV energies. And then you can use, at the highest energies, you try to explain the process in a self-consistent way as either synchrotron emission or inverse Compton emission or a pion production in the jets. Okay, and so these jets, as I mentioned earlier, they're across all size scales, and they are not necessarily extragalactic, because we are also seeing jets of microquasars, which are galactic sources, which actually give you the opportunity to study jets from much up close, and it could inform us about these extragalactic jets on a different scale. So I just wanted to share a few sort of incredible properties of these objects. So if you look at the plot here, which shows you the power, this is some sort of an energy flux, energy per second as a function of energy. And what you see, first of all, is that these objects continue on. So there's no cutoff. They have very high isotropic luminosity, which is like 10 to the 48 ergs per second. For gamma ray sources, for such high luminosity, you would expect to see gamma-gamma absorption, and the source would be opaque, but you don't see it. So this gives us the idea that these sources are coming from objects that are Doppler boosted along our line of sight, and you see relativistic effects in these objects. So here, for example, the fact that you don't see, you see these gamma rays with such high luminosity tells us that these are not isotropic sources at rest, and you actually have some sort of boosting along the line of sight. And we are seeing this now with measurements at other wavelengths. So if you look at an image, for example, of a so-called active galaxy taken with radio imaging, what you see is across several years, and this is light years on the plane of the sky, you're actually able to measure the speed, and you image these knots. You see a central knot here, and you see the motion of these knots. You have direct evidence that these knots are actually superluminal. So on the plane of the sky, it seems like they're moving faster than the speed of light. And that is as a result of the geometry of these objects, the fact that they're beamed in our direction and the particles are relativistic. And in these cases, you can even, there's actually direct imaging now with these instruments where you can measure, you can track the motion of these objects. Okay, so let me show you a few more of these results, and then I will, in the next 10 minutes, try to wrap up. So I wanted to show you the kind of measurements you can make with these light curves. So these are, as I said, sources show short time scale variability. So here is a measurement, 15 minutes time scale, which can give you a hint on the size of the emission region just from causality and light travel time. Here is another one where you have a giant flare, which is actually a magic and veritas measurement, where you can see light scale to time in 2-minute time bins, and you can use this information to estimate the Doppler factor, so how fast is the relativistic boosting happening. And for such, the theory behind such short time scale variability in the blazar jet, there's some work happening where the idea is that you're probably seeing these plasmoids because the size of this emission region for a black hole that's 10 to the 8 solar masses is about 10 times the Schwarzschild radius. So probably these are these plasmoids that are in the jet and where you have magnetic reconnection. And so this is an image which I find really fascinating because on the left-hand side, you have a measurement by MAGIC and Veritas during this exceptional flare broken up into 3 different energy bands. But on the right-hand side is a computer simulation of that same flare. So it's a theoretical modeling of how you might produce short time scale variability using this kind of model where you have this plasmoid that's in the relativistic jet of the blazar. So, this is a very difficult thing. I mean, we have measurements, and that's actual fact. That's the data. But how do you model this? How do you explain the short time scale variability? And so that's work that's happening, and I'm personally, keeping an eye on this to see what's happening in the future. So I'm going to skip this because we don't have so much time, but I just want to say that we are able to do a lot of interesting science with these TeV instruments, and particularly with Veritas, which is what I work on. We look at surveys, we look at point sources, we do a lot of detailed monitoring. And I just wanted to maybe take a couple of minutes to talk about another system, which is in our own galaxy. And so these are power sources that are either supernova shocks or some kind of collapse of a massive star in our galaxy, where we know that you might have a situation or an environment that can give rise to very high sort of shock speeds and shock physics, and where you can actually accelerate particles to high energies. So one such system, and this is work that postdocs in my group have done, is basically looking at this one source, Milagro J1908, and this is to give you an idea of the kind of detailed study you can do. This is a very interesting source because it's in our galaxy and is very close to a microquasar system, which we know is a very high energy emitter. And we have hint from Lasso and Hawk that these could be pevetrons. And you can, I don't know if you can see at the back, but here's a pulsar and here's a supernova remnant. So we don't know if the emission is due to the wind of the pulsar. So the pulsar is rotating, it's losing energy, and then you have this wind, which is accelerating electrons, or it could be due to a supernova remnant, which has molecular clouds and hydrogen, and you might have hadronic processes. And so what we do is we try to make images that are resolved in energy. So you can see here is the lowest energy in gamma rays, which is in Fermi lat. This is Veritas, and then this is Hawk, which is this Water-Cherenkov detector. And you can see that there is a dependence of energy morphology. So the maps look different. And maybe I've spent too much time looking at this, but you can at least see that at this energy band in Veritas, there is the highest energy emission is actually coincident with the pulsar itself. And so, simplifying this extremely, you can then build what we, again, as I mentioned, a spectral energy distribution plot. You see here across the broad energy band in Fermi. And then you have to do modeling, because it's at this point, with the data you have and the physics that you know, can you explain this emission with the physical process? And we think it's due to, it's being powered by the pulsar itself and not the supernova remnant. Okay, so maybe I have 5 minutes. 5 minutes, okay. So maybe I'll just end with what's in the future. Okay, so I hope that you at least now have sort of a flavor of where we are coming from. We are sitting on a huge amount of exciting data. So what's in the future? The big sort of thing that's happening in the world of gamma ray, high energy gamma rays, is the Cherenkov Telescope Array Observatory. And the main sort of idea behind CTAO is that if you have a light pool, the Cherenkov light pool on the ground, which is about 100 to 150 meters, currently we are missing most of the light. So in order to take advantage, in order to be able to be more sensitive, you really need more telescopes that can sample more of the light pool and be sensitive to lower energy thresholds, so more collection area and more light. And so that's simply basically the idea behind Cherenkov Telescope Array Observatory, where you build different telescopes of different sizes, and you can extend the coverage, so you can go from tens of GeV to hundreds of TeV. And in fact, that's what's happening now. And there's the large size telescope, which is already in operation, and then the medium and small. And then for us, for me personally, and the group, and some of us in the US, we are also kind of looking to beyond the future here with this dual mirror instrument, which could push the limit of the technology. The design drivers, I think we from what we know, I think that we want much better sensitivity, full sky coverage, wide energy range, and then we want arc-minute angular resolution so that we can image these objects. And and talk about the morphology or what is the spatial distribution of particles across the sky. So that kind of is going to help us. And these are basically the status. We are, as I said, we are already in progress. There's work happening in the north. There's also some work happening in the south. The north side is much more advanced. We have the first LST is already there and producing great results. I mean, even with the prototype and the early results, there was a measurement of the Crab flux and the Crab pulsar, and really remarkably also the detection of a new class of object. It's RS Ophiuchi, which is a high mass red giant binary system which went into an explosion and was detected in high energy gamma rays. In the southern side, work is just starting and infrastructure is happening, so there is a way forward. There will be work done in the future. And then I promised to tell you a little bit about what we are doing. And in the US, there is this sort of a prototype development to build a new kind of telescope, which is a dual mirror. So the one thing you see here is there are two mirrors, and the camera itself, which is the detection unit, is at the focus of the second mirror. So the main thing to notice here is that because of the dual mirror technology, you're able to, just from the optics, open up the sky, so you have a much larger field of view. And because you have a very compact focal plane, you can actually be able to get many more pixelation. So you're able to build a camera that has much finer pixelation, and so you can actually be able to image a much finer resolution, so to speak, just because of the fact that you have a much smaller sort of a focal plane, and your instrument can be much finer resolution. And so this gives you the ability to have a better gamma ray PSF across the field of view and do the kind of morphology studies that we want. And what we are using now is this silicon PM sort of solid state devices which have very fine pixelation. So this is still work in progress for the future, but the hope is that you can do an order of magnitude better sensitivity compared to current generation instruments. So to end, I think I just want to end with sort of the future vision. So in the US, we've been talking basically through something called the Astro 2020 Decadal Survey. It was an exercise by the funding agencies and the institutions to ask the question, what are the key scientific challenges for astronomy and astrophysics in the next decade? And there is a report that was written by the National Academies, and you can look it up, but the goal was to identify the most compelling scientific goals for future investment. And you can see here, across the 4 different messengers, gravitational waves, neutrinos, gamma rays, and cosmic rays, the blue are the existing projects, the green are the endorsed projects, okay? But then for the students in the room, basically you can look at what is missing. So there are missing capabilities, particularly in the medium energy band, as well as there's this big sort of communities with missing instrumentation that we should think about for the future. So this is kind of like a comprehensive view of the current and future abilities. So just to end, I think that the takeaway here, that the field right now is kind of at its very rich. We've learned a lot. We've made a huge progress in instrumentation and done a lot of science, but the future looks really bright with CTA. The Cherenkov Telescope Area Observatory, and this is again a technical plot, but you can see the sensitivity reach here is going to be much better than current generation instruments, both for integrated sensitivity as well as sensitivity to transients. So we should see an order of magnitude improvement across the energy band, and also a dramatic reduction in observation time. And so I'm hopeful that this is right around the corner, and some of us are actually working on this. And I just want to end by thanking you, and also to the funding institutions and various people who've helped me. Thank you.
Thank you very much, Reshmi, for this very nice presentation. There is time for questions and comments.
Hi,
Hi.
thanks for the talk, first of all. I have actually two questions. And the first one, in the Milagro source that you
Yes.
showed, you said it was a Pevatron candidate, if I didn't misunderstand. The spectrum you measured and and the modeling you did afterwards is still compatible with being a Pevatron candidate or not anymore?
We don't think so.
Okay.
I think that from the spectrum, there's a cutoff.
Yes.
So we don't
Mhm.
see
But-
this to be a Pevatron candidate. Now, are we seeing the same source that Milagro is seeing? It's hard to say because the Milagro source was very extended. So you can see that the Hawk actually has a nice measurement. Yeah. So the answer is that it doesn't look like it's a Pevatron candidate because there's a cutoff in the electron energy.
At
And-
which energy? Do you remember more or less?
Yes, I do remember. So the Hawk image is at 100 TeV, right? The spectrum goes up to 100 TeV for Hawk. For Veritas, it's about 10 TeV. So there is a cutoff in the spectrum.
Okay. And the other question is more a curiosity, and it's once CTA starts becoming a reality, what is the future for Veritas?
For Veritas?
Yes.
Yeah, it's a good question. So I think that LST1 has already shown the amazing sensitivity, even with a single telescope. I think that when the other 3 telescopes will be built, I think Veritas will be obsolete, right? However, I think there is a time where you need an overlap of instruments. When the new instruments are coming online, the old instruments are proven and well established. And so you have confidence in their measurements. So I think there's always good to have a period of overlap. I think the real challenge is, of course, with the scientists, because you have a pool of scientists who are working now on both. The other thing I think we should keep in mind is that when the new instruments start operation, there will be a lot of exciting things to see. And they will have a science program which will be competitive, and you want to go for sources that are, the most exciting. The current instruments, you could use them in parallel with much more focused observations, and where you can just spend all your time on one dedicated source and then try to establish a long baseline. I think that's good in both, but it can't be forever.
Okay, thank you.
More questions? Comments?
Yeah, Reshmi, thanks for the talk. So for many years, it was thought that supernova remnants or supernova explosions and remnants were the places for
Yes.
cosmic ray acceleration in the galaxy, right?
Yeah.
Later, it has been suggested that pulsar would also contribute to that, and also clusters of massive stars.
Yeah.
But it seems that supernova remnants, supernova explosions are needed in the modeling to produce these pevatrons in these places. Now, more recently, there has been the detection of these binaries
Yes.
that also are seen at TVs and hundreds of TVs, right? And even above that, those energies. So what's your feeling about
Yeah.
where are we? Because it's amazing the revolution that is happening in the field, and we have more sources, but we are still lost, right?
So this is an example of supernova remnants being ruled out as the highest energy, because you can see a cutoff in the spectrum. You see, I mean, there is hadronic emission, and there is pi zeros happening. This is a famous supernova remnant, IC443, which is extended and which we were thinking could be a Pevatron accelerator. But I think you're right, we have ruled out several of these northern supernova remnants as the highest energy. Personally, I'm very excited about the results that are coming out with the binaries, the microquasars, which have jets, and in particular, the 2 recent ones that have been discovered in the galaxy at TeV energies and beyond, where you can see the evidence of shock acceleration in the jet and interaction. Now, they could, I think, if you work out the energetics, could explain the cosmic ray density, energy density, but Are they Pevatron accelerators? I think we have to wait and see. There are some candidates for, I think, some that are promising, but yeah, we're still looking.
I make a comment myself. Maybe it's more like we do see that at least some of them, they can reach PV energies,
Yeah.
but the question is the energetics of the population at PV energies, whether they can indeed reach the observed PV
Yeah,
cosmic rays.
that's right. That's correct.
More than for questions, comments? Okay, so I have a question myself. You showed this source 1908.
Yeah.
I think it's the one which is next to SS433, this very powerful microquasar.
Yeah.
And you said that when you look only at 1908, you don't see significant PV, like PV emission. You don't expect significant PV emission. But you mentioned the Milagro source. Was the Milagro source probably also encompassing the microquasar? Because I guess that it was larger.
Yeah. The microquasar, so it's about a degree away from the microquasar.
Okay.
The microquasar is very extended, and Milagro sees this extended giant emission from, I think maybe the Milagro wasn't able to, this is basically named after the Milagro source. And you can see here I think the black circle is giving you the size of the Milagro source. The white is just, the white contours are CO maps, so matter. So to answer your question, Veritas, this image is Veritas, and Veritas, this is not SS433, this shows you the Milagro J 1908. And so here, you're only seeing with Hawk now just the SS433 image and not the microquasar, which has been blocked out, which is to the northeast image. So I don't think this is emission from SS433. It really is from the Milagro source.
But I mean, when Milagro saw the source,
Yeah,
Milagro was already, let's say, pointing away from SS433.
Yeah.
So it was not including that source.
It was not including the source. I mean, there could have been some emission if in an extended analysis, but it was really not the SS433 source.
Okay, so this time for some question or comment. If not, let's thank Reshmi again.
Thank you.
Thank you.